All right, so welcome to the software design track and welcome to this particular talk about design patterns, facts and misconceptions. Give me 10 seconds to introduce myself. My name is Klaus Iglberger. I'm perfectly happy if we stick to the first name because I realized that many people cannot pronounce my last name. So I'm Klaus and I'm working as a C++ trainer and consultant. As such, I'm actually talking a lot about software design patterns. And I also had the pleasure to talk about software design at a recent CPP chat episode. I was invited to talk about the solid principles together with Tony van Oort, Phil Nash, and John Culp. This was actually quite a lot of fun. I really liked the discussion. And so at the end of this episode, I asked the question, why aren't we actually talking about software design more often? Why do we talk so often about language mechanics, features, C++ standards? And both Tony and John kind of confirmed my suspicion because software design is hard. That is actually the really hard part of developing software, creating the right structures, etc. And both said that in software design, there is no 100% answers anymore. And so there is a lot of discussion, of course. Yeah? It always depends. Still, I believe it's really important to talk about software design and obviously also about design patterns. And so let's talk about these two things, software design and design patterns. However, allow me to add this little disclaimer. Of course, all the things that I'm talking about are based on my personal subjective impressions, experiences, and opinions. Now, hopefully, my experience and my opinions help you to get a better understanding of software design and design patterns in particular. But still, you may have a different opinion based on your experiences and based on your expressions. And that's perfectly fine. Indeed, it may be absolutely reasonable to have slightly different opinions once in a while, but this is the reason why we should talk about this. This is the reason why we should experience each other's experiences and learn from each other. Simply because there is no definitive answer anymore. It is hard. And so very often the answer is, it depends. But I believe this is why it's actually fun. Now, this is why I like this topic and why I believe this is actually so important. Not just because it's fun, but really because I believe it's important. Now, to get this started, I actually want to talk about make unique. I know, a pretty small and apparently innocent example, but this will actually take us very close to software design and design patterns. You'll much better understand what this actually is. And so I'm making three statements. Make unique improves exception safety. Make unique fulfills the single responsibility principle. And make unique is a factory function. All right, I'll now tackle them one by one. And we'll actually see if these claims are actually correct. So first, let's talk about whether make unique improves exception safety. What I mean by that, what the community means by that, is the following example, or is visible in the following example. You may have a function called process that may take two unique pointers. This process function is at some point called, and I'm creating these unique pointers directly. So I'm newing a widget, put it into a unique pointer. I'm newing a second widget, putting it in a unique pointer, and call the process function. Now, interestingly, this actually might work in many different ways. So there are several possible orders of operations. For instance, we could first create the new widget 1, then pass this to the unique pointer, create a unique pointer. Then we could turn to create the second widget before we put this into a unique pointer. Now, indeed, the compiler was allowed to rearrange these operations. So it could be that the compiler chooses to first create the two widgets. But if the second widget, for some reason, throws an exception, for some reason fails, indeed, the first widget, that resource is lost. And we've just produced a resource leak. So make unique may actually be an advantage in that situation. But this reordering of operations is actually no longer an issue since C++ 17. The compiler may no longer rearrange these operations arbitrarily. It may still first create widget 1 and then 2, or the first 2 and then 1, but it is not the compiler is not allowed to rearrange the new such that we have an exception safety problem. Therefore, yeah, it was once upon a time an exception safety improvement, but no longer. So that is a thing of the past. Now, Make Unique fulfills the single responsibility principle. Let's take a look at the single responsibility principle. What is that? This is now the Wikipedia article, and it describes the single responsibility principle in the following form. The single responsibility principle is a computer programming principle that states that every module, class, or function in a computer program should have responsibility over a single part of that program's functionality, and it should encapsulate that part. All of that module, class, or function services should be narrowly aligned with that responsibility. This seems to be obvious. Everything should have one responsibility. But over the years, the statement was kind of decaying into everything should do just one thing. And that seems to apply perfectly for Make Unique. It's doing one thing. It creates, let's say, a widget, new widget. That's what it does. However, that's not exactly what the single responsibility principle actually says. I tried to explain this in a talk last year, where I actually talked about the solid principles, the talk that then led to the CPP chat episode. And in short form, I would say this is what SRP truly is about. The single responsibility principle advises to separate concerns, to isolate and simplify change. That is a little different indeed. I do not talk about a single responsibility, and that name is truly not a good name. It is more confusing than it actually helps. And separation of concerns is something that definitely has a slightly different idea, because that ultimately leads in the direction of software design. We should separate concerns in order to be able to change more easily and extend more easily, and then perhaps even test more easily, if you want to talk about testing also. So software design, what is that? The Wikipedia article says a lot, but I think this is very, very high level and hard to understand. So I took the liberty to ask an expert, Robert Martin. And this is what he says, of course, in the book, Clean Architecture. So first of all, he says, I will assert that there's no difference between architecture and design. None at all. Okay, so design and architecture are indeed, as we'll also see, very, very similar. There is a very blurry line between these two. However, then he continues, the goal of software architecture is to minimize the human resources required to build and maintain the required system. So ultimately, the goal is to actually enable something to build at all. If we need hundreds of developers to build the smallest things, something would of course not be correct. But in this formulation, I believe people may still get the wrong idea. It's very open to interpretation. So allow me a shot to define software design a little more precisely. My perspective. Software design is the art of managing interdependencies between software components. It aims at minimizing technical dependencies and introduces the necessary abstractions and compromises. So indeed, I'm very much convinced that it's an art. It's not a science. Definitely, it's a lot about gut feelings. It's a lot about experiences. It's a lot about the soft things that we software developers do. It's not something where you can give 100% answers indeed. But I'm very convinced that it's always aiming at minimizing dependencies. Dependencies, the thing that makes software development so hard. Dependencies, that is the problem that we usually face. This is what makes it hard to change or extend software. And so definitely software design is basically the thing that tries to help here. And so it usually introduces some kind of abstraction, something that enables us to overcome these dependencies, but also there may be compromises. Sometimes it's just not perfect. We ourselves might not be particularly happy with some solution. Sometimes we might refer to that as technical debt. If that is software design, however, and perhaps in short, software design is the art of managing dependencies and abstractions, then I don't see any connection anymore to something like Make Unique. So that is the implementation, the definition of standard Make Unique. The function that simply says new T, that's essentially what it is doing. This standard make unique function does not resolve any kind of dependency, not a single one. If you have this in your code, you always know for sure that you will get a T, and you always know that this will use new, always. And so it definitely does not provide any semantic abstraction. You don't have the opportunity to customize this function. You cannot overload it. The choice of forwarding references is pretty prohibitive. Overloading does not really work technically. And specializing make unique, we just don't specialize function templates. So no, it definitely was never designed as a customization point. It's not an abstraction. And so from my point of view, this truly has nothing to do with software design. It never helps at any point in that process. And so it also has nothing to do with design principles. It never helps me to separate concerns. And so yes, it does one thing, but no, I would not claim that it fulfills the single responsibility principle. Which now leaves us with the third statement. Make unique is a factory function. And yes, factory function. We should first clarify a little bit what a factory function is. And I've now picked Core Guideline C50, which says use a factory function if you need virtual behavior during initialization. Now, what this core guideline actually wants us to do is to not call virtual functions during construction destruction. So for instance, this create my thing would create a my thing class, but it would first call all the constructors that are necessary. Potentially there's many in a hierarchy. And then afterwards, after make unique is done, after we have fully initialized the object, we might call a virtual init function and then return. So this here is the virtual function call. In that form, it is safe. This is what the factory function is supposed to achieve here. But again, the question is this truly software design? Does this truly help with any kind of dependency? And so I actually, again, asked Wikipedia. And there's a very nice article about factory, the object-oriented programming site. There's actually several different pages. But this one very nicely explains that some sources refer to the concept of the factory as the factory pattern, while others consider the concept itself a programming idiom. And probably most importantly, the general concept of a factory is often confused with a specific factory method design pattern. So I believe it's time enough to actually take a step back, actually talk a little more about design, architecture, and implementation details. So I would say in the center of it all is the thing that we're now talking about, software design. Software design, that is basically the decision about the small entities, how they depend on each other. This is also the things that may be changed a little easier in comparison to architecture, which we'll touch in a second. And this is the realm of design patterns. And just to name a few, the famous ones, Visitor, Strategy, and Observer from the Gang of Four book, which is that book. That book that released in 1994 gave us 23 of the most commonly used design patterns. Above design, however, is what we call architecture. As I said before, there is a very blurry line between the two. And this is why many references actually fall into both realms to some extent. But very often you use the term architecture to mean the big things. How do modules depend on each other? And I don't mean the C++ modules. I mean the big agglomerations of many classes, functions, etc. And very often we argue that this is decisions that are a little harder to change. Also, might not be true anymore with microservices, but still, there's architectural patterns. Below all this is the implementation details. That is now how we implement the design. This is where we actually see which features are used, which C++ standards are used, how we actually solve particular problems. New, malloc, whether we use class or struct, lambdas, all of these details. There's a lot of information down here, a lot of knowledge, of course, but it's indeed below the question of design, below the question of dependencies. We note, at this point, I talk about design patterns. And then at this point, I talk about implementation patterns. That is a term that I've not seen before. That is a term that I kind of made up. because the other term is a little vague also. And I'm talking about the term idioms. An idiom is not necessarily an implementation detail, and an idiom is also not necessarily design. It can be both. For instance, in C++, we're talking about the non-virtual interface idiom, or short NVI. That is an example of the so-called template method design pattern. We also talk about the pimple idiom, for instance, which is the simplest case of the bridge design pattern. But there's many, many more idioms, like the temporary swap idiom, or the RAII idiom, or enable if, etc. There may be many, many idioms where we say this is idiomatic usage of the language, but that still have nothing to do with design, with interactions between entities, with minimizing dependencies. So the term idiom is not quite clear. And so I use implementation patterns as a distinction. Now, design. We talked about make unique. And let's take a look at software design patterns. Wikipedia lists a lot of software design patterns, but it also lists a couple that are kind of questionable. For instance, here, resource acquisition initialization is named as a design pattern. I would raise a big flag here, in C++ at least. I don't see how that actually deals with dependencies. It deals with automatic resource management, which is super valuable, but it doesn't help me to detangle any entities. It's not about decoupling. But there's many more, like singleton, for instance. Yeah, of course, one of our favorite design patterns, or infamous, but I would argue, and this is a claim, that singleton also is not a design pattern. Yes, I know it's in the design patterns book that I just mentioned, but I don't see how it detangles or decouples any entities. That may actually be the reason why so many people have a problem with it. It doesn't decrease dependencies. Actually, it may increase dependencies. So it might actually be against our intuition to properly design. But there's many more, like multiton. And I would also claim that memento, another one of these GoF patterns, is actually not a design pattern. There's no dependency management at this point. It's an internal implementation detail, nothing more. There's actually more, but just to give you an idea, there is still the need to communicate. There's still the need to discuss certain issues. So, but I now return to the design patterns book and actually take a look at the pattern that we actually have in mind when you talk about factory, which is the factory method design pattern. It's one of these creational patterns, one of the 5 described in the book. And this is what the Gang of 4 says about this factory method design pattern. Define an interface for creating an object, but let subclasses decide which class to instantiate. Factory method lets a class defer instantiation to subclasses. So, what does that mean? Well, that is what the Gang of 4 actually shows us as a UML diagram for the factory method design pattern. There is some creator, there is a concrete implementation of that, and we are creating some concrete products, but at this level, we only know about abstract products. This is truly a design pattern. Why? Simply because I can draw a line, a clear line that I now describe as an architectural boundary. I can clearly distinguish between something that I consider to be high level, something that I consider to be stable, something that does not change often, and a low level that I consider to be malleable or volatile, things that change more often. There's a clear distinction between these two sides. And that is what this truly makes a design pattern. I really deal with some kind of dependency. And I also have a clear inversion of dependencies. So indeed, really a design pattern. But I don't really see this in Make Unique. So just to summarize, the purpose of a design pattern is to introduce a fitting abstraction for a well-known problem. In the case of a factory pattern, the factory method design pattern, it's just the problem of creating things. The name of a design pattern conveys the intent of the abstraction. So if I talk to you about factory method design pattern, you should immediately have an idea what I have in mind. The same is true for, if I say visitor, observer, strategy. You should always have a pretty clear idea what I have in mind when I say that. But standard make unique doesn't have that. Sure, it has a name, true, but I cannot draw a line here. I cannot really see a high and a low level. I don't distinguish between the two. I don't separate concerns. So from my perspective, it's merely an implementation detail. It's definitely not a design pattern. So to summarize, make unique is a factory function. That's just the terminology we use, and that is confusing. That is why people always stumble across that and don't really know what's happening. But it's not a design pattern. I consider it merely as an implementation detail. All right. However, there is many other misconceptions about design patterns. For instance, design patterns are limited to runtime polymorphism. Design patterns are limited to object-oriented programming. And design patterns are language-specific idioms. And last but not least, design patterns can be recognized by their structure. Perhaps you've heard these misconceptions too. So I actually, just a few weeks ago, again, heard a couple of these misconceptions kind of all together. And so allow me to show that indeed all of these are pretty bad misconceptions, something that you should not consider for yourself anymore. And now we go to one of these classic gang of four design patterns, the command design pattern. Command introduces some kind of abstraction for some action, something that it can be called. So the base class command has an execute function that of course can be implemented in any way you seem fit. That execute function usually then triggers some kind of action, and indeed it can be anything, and it could be an action on some receiver. However, again, clearly it's a design pattern. There is a high level, the command abstraction, and there's a low level, the concrete implementation details. So I could draw a line in between. This makes it a design pattern. However, yes, of course, this is the object-oriented form. That is what the Gang of Four describes in their book. But this is not the only way you can implement a command. No, you've actually seen this in many other forms. For instance, you've seen it in template form. So some function that takes a template argument up for some operation. That actually may be the command design pattern. And as I said, you may have seen this a lot of times because we use that in the standard library quite extensively. For each, the algorithm. I may have a vector of integers, some numbers, 1 to 7. And for each allows me to modify this, not modify, so to do something with these numbers. I could multiply them by 10, I could print them, I could do whatever I want. I can apply some action to all of these elements. That feels indeed like the command design pattern, just not in an object-oriented or a dynamic polymorphism form, not a static polymorphism. Absolutely. However, of course, there's more design patterns, like, for instance, the strategy design pattern. Strategy is different. With strategy, the idea is that I can configure the behavior of some context. So I pass a strategy, classically by means of a pointer, to some context, and that context can now use that strategy from now on. Runtime configuration, we call this dependency injection. And that separates concerns indeed, because now anybody can implement a new strategy. This context doesn't have to know about any particular implementation. There's many possible strategies possible. There is indeed a clear separation of dependencies, a clear separation of concerns. A design pattern. But again, in the end, it's a base class and a deriving class, or many deriving classes. And again, we could actually implement this by means of functions. So a function that takes some operation that actually might be the strategy design pattern, like, for instance, accumulate or reduce. Standard accumulate takes, again, iterators to here a vector of integers, and it might now sum all of these up by means of plus, which is kind of the default behavior, of course. That plus here, that now might be a strategy, because we, from the outside, configure the behavior of this algorithm. We inject the dependency and actually now make accumulate truly work in a way that we intended to work. Dependency injection. However, of course, you're confused. Didn't I just explain that this is the command design pattern? Well, it is confusing. It really is. But it depends. If you have these two design patterns directly next to each other, and if I would get rid of the names, you would not see a difference. Structurally, these two are 100% identical. There's no difference. Both in the classic form are based on one base class and many derived classes. And if you take a look at the algorithm form again, the command design pattern and the strategy design pattern, then again, structurally, they're 100% identical. It's the same thing. In both cases, I pass some callable. In the first case, it's a lambda, and the second, it's a function object, but still, it seems to be pretty much the same. So, what is the difference? And so, again, let's take a look at the original book, the Gang of Four book. That one says about the command design pattern, encapsulate a request as an object, thereby letting you parameterize clients with different requests, cure or log requests, and support undoable operations. All right. And about the strategy design pattern, they say, define a family of algorithms, encapsulate each one, and make them interchangeable. Strategy lets the algorithm vary independently from clients that use it. There is a couple of keywords like undoable that actually might help us to distinguish the two, but it might not be entirely clear. So allow me to shed a little more light on the difference. The command design pattern specifies what should be done. So if you actually would describe this as a what, like for each, what should I do with these elements, then it seems to be a command. The strategy design pattern, on the other hand, specifies how something should be done. How should I accumulate the elements? How should I proceed in this algorithm? It's different, yet not so different that it's easy to distinguish. Indeed, there is a blurry line between these two, indeed. Now, there may be a couple of telltale signs, like a command is indeed often equipped with an undo. Strategy is not, usually, but it is a little hard to truly distinguish these two. Therefore, here, the example. What should I do with each element in for each? How should I accumulate the elements? That may be the telltale sign for you. But as a takeaway, the intents are different. The structure is the same. The intent is different. So the intent of the command design pattern is to specify what should be done, whereas the intent of a strategy design pattern is to specify how something should be done. So please remember that the difference between design patterns very often is not the structure, it's their intent. Pretty much all classic design patterns look very much alike, but the intent is always different. And based on this intent, you name them. With a name, you communicate the intent. However, probably most important here is, please remember that design patterns are neither limited to object-oriented programming nor dynamic polymorphism. We've just seen that strategy and command work just as well in a static context, in a template context. So no, it's not just object-oriented design patterns. These two definitely are much more general. There's one takeaway that perhaps you can think about. Since the name of a design pattern should convey some intention, some intent, it actually may help to use that name in your code. So for instance, for each, instead of calling this unary function, we might actually call this, for instance, unary command. And in case of accumulate, a binary reduction strategy would help to understand that. Sure, it's binary. We want to reduce, but it is a strategy. Allows us to configure the behavior from outside. All right, so indeed, structurally, design patterns are very, very often very, very similar. However, there's a few other misconceptions about design patterns. Design patterns are outdated and design patterns have become obsolete. And this is actually things that only recently I stumbled across. So I gave a talk about design patterns a couple of months ago, and that was one of the reactions in after uploading this to YouTube. Really? Design patterns in 2021? And that was kind of sad indeed. Apparently, somebody did not realize how important design and design patterns in particular truly is. I actually believe this is responsible for the success of your project. Good structure, good use of design, and the design patterns, of course, may indeed be the decisive piece. So I claim that design patterns are pretty much everywhere. If you've not in the last week used any kind of design pattern, and either you have very limited knowledge about design patterns or you didn't write any code. No, they're pretty much everywhere, including the standard library. And so here's a little challenge for you. I claim that there is many different design patterns in the standard library. Indeed, many. Name as many different design patterns as possible that are used within the C++ standard library. And of course, I know 20 seconds are not a lot of time, but if you come up with a couple, then this is definitely a good sign. So go. And of course, if you're watching this talk in the video, you can of course stop, really think about this, get an opinion, you collect them, and then proceed. We'll actually talk about what is possible. And notice the beautiful animation. It took me an hour to do that. Okay, so let's take a look. So I have collected them myself, and no, I actually did not collect all of them. I just wanted to give you a pretty good impression on there is a lot. So let's start with the low-hanging fruits, the ones that I've basically already explained. The strategy design pattern. It's used in hundreds of places throughout the standard library. Virtually, most of the algorithms actually use that, accumulate. Then, however, also containers use that extensively. StudVector takes an allocator. That allocator is a strategy. Sure, because I can configure that particular behavior allocation from the outside. Dependency injection. Very elegant indeed. Of course, this is true for all containers, and some even have many strategies like unordered set, hash key equal, and allocator are strategies. And unique pointer, that is also something that uses a strategy. The second template argument, the one that we do not use every time, the deleter. The deleter is a strategy. So there is probably hundreds of strategies throughout the standard library. It definitely is one of the most important design patterns we have available. But as I also explained before, we have command. So for each or transform are two things that come to my mind. For each is kind of simple. Transform may be a little more debatable, but I believe that we apply an operation to all the arguments. So truly resembles the what should I do with all the arguments. What, not how. All right, but then there is also obviously iterator. Iterators, they're so obvious that we don't even think about this as any design pattern anymore. So all the kinds of different abstractions, random access, bidirectional, forward, input iterators, and of course also output iterators, that is a design pattern. And really, it's about separating concerns. I can very clearly draw a line. Algorithms are on top, the high level. Containers, in this particular case, represent the low level. Iterators serve as the dependency solution between them. They serve as the glue, but also as the abstraction layer. Concepts, by the way, exactly serve that purpose. The named template arguments that we have. It is a design pattern used pretty extensively. Okay, number 4, the adapter design pattern. Now, of course, when I name it, you immediately have a pretty good idea what I have in mind. Of course, there's 3 classes in the standard library, even in the original STL, that are adapters: stack, queue, and of course also priority queue. These classes are not containers, but they adapt a container. They give it a new interface, based on what you want to achieve. Stack, of course, deals with restricting a container to only putting something to the end, push, and of course, taking something away from the end, a pop. You can't even iterate over these elements. Very restricted interface. A queue allows you to add to the end, but pop from the front. And a priority queue is pretty similar in that it adds a priority value to all the elements. But there's one more. There is this one here, PMR polymorphic allocator, which in C++17 represents the allocator of a PMR vector. That polymorphic allocator serves as an adapter for memory resource classes. Many classes that inherit from memory resource in order to implement new allocators. So we don't have a new vector class, but we have an adapter that helps us to reuse the existing class, but to change the way we deal with allocators. Really beautifully done indeed. Which, however, now leads me indeed to another example using allocators, and that's now an example for the decorator design pattern. I don't know if you have actually tried out C++17 allocators already, but here's an example. You can create an allocator, in this case, a monotonic buffer resource that is configured somehow, but also takes another allocator. So in C++17, you can create hierarchies of allocators. So what should the monotonic buffer resource do when it's out of memory? Well, it should just ask the other allocator. So you can very, very beautifully build hierarchies of allocators. And that is the decorator design pattern. Decorator doesn't replace an implementation, but decorator decorates something. It extends an implementation, builds on the existing one. Side note, yes, this function here, null memory resource, actually returns a singleton. But as I said before, I don't count this as a design pattern. It's an implementation detail. It doesn't help us to detangle. It just allows us to have one instance of the thing. All right. But then there's one more. Now, since we've now talked about the memory resource base class, here it is. That is the memory resource base class, which, however, proves to be a pretty impressive example for the memory for the template method design pattern. The template method design pattern separates the concern between virtual functions and the public caller interface. So a memory resource has a public allocate function, which is non-virtual, which in a sense calls a private virtual function called doAllocate. So I'm separating the concern. I am suddenly able to change things internally a little easier without changing the public interface. So again, something that helps us to detangle, something that helps us to deal with dependencies and to change things easier and extend things easier. So C++17, who would have thought that there's so many classic design patterns involved? Indeed. All right. Then there is actually a couple of examples for the proxy design pattern. And I'm now, of course, using the most famous one, the one that nobody likes, the one that is infamous, vectorbool. If you access a value of a vectorbool by means of the subscript operator, what you do get is not a reference to bool. Nope. You get a proxy object that represents that bool. Vectorbool actually doesn't store booleans, but it is implemented as something that helps to reduce memory. So vectorbool stores single bits for every byte, which of course doesn't really work like that, but it kind of works in that way that it indeed uses bits, but stores something slightly different. But because it doesn't store bools, because with that operator you expect to access a bool, it returns a proxy that pretends to be a bool. You don't see it, not directly, but it behaves a little differently. And that's what many people don't really like. But it's an example of proxy. And very similar is actually, what bitset delivers to you. If you call this operator on a bitset, you do get a reference in the non-cons version. That reference, again, is some kind of proxy. There is no bit. You cannot access a bit directly. Therefore, must be some kind of proxy object that pretends to be that bit, but it's not. So, well, proxy design pattern. But then there's actually a couple of slightly more complicated ones. So I now dive into standard function a little bit, just to show that, again, there is a lot of design patterns involved in that implementation. Now, you don't have to understand every detail, but I now basically just show the very, very basic ideas. So here is the forward declaration. This is basically the base template, but we have to specialize it in order to make sure that we know that the given thing is a type, a specific type, a function type. So something with a return value R and something with some arguments. So that is exactly what standard function expects. Some function type, you know about the R, and now we also know about these arguments. What a standard function now does is, it allows you to pass virtually anything, any kind of callable that hopefully adheres to that function type. So some f. That f is actually stored, however, in form of a model. This model is a nested class in the private section of the class function, a model class. A model that is instantiated for the purpose of that given type, maybe a lambda, maybe a function object, something. That model stores that fn. Still, standard function could not store the model. It could not store the f directly. It could also not store the model. It needs something else to actually store that. And that is what it does by means of an internal base class, a concept base class. A base class that all models use, all the models publicly derive from this concept. And that concept now represents the abstraction of a callable. That is indeed a design pattern. This internal hierarchy, this concept and that model, this is called the external polymorphism design pattern. Whatever I get, I will put it into my own hierarchy. I don't expect that a thing behaves polymorphically. I will make it behave polymorphically by means of creating this inheritance hierarchy in my own private section. So external polymorphism is not one of those classic gang of four design patterns. It's a design pattern from 1996, so a couple of years after the GoF book. It was published by Cleland, Schmidt, and Harrison in that paper. Now, I do recommend the read. It's a description of a classic design pattern indeed, but a seriously valuable one. Seriously valuable indeed. So the intent, in short, is to externalize dynamic behavior, to create a separate hierarchy in order to make any type behave polymorphically. Super valuable indeed. However, there is more. In standard function, we now store this thing that we have, this concept, in form of a unique pointer. And we give it a name. We call it pimple. So we now store that thing in an abstract form, in form of a pointer to concept. But that name is something that you might have heard before. We now manage that, and we now kind of bridge, by means of this hierarchy, the gap between our abstraction here and the real implementation that is represented by the given callable. bridge. That is the bridge design pattern. The simplest form of the bridge design pattern, we call this the pimple idiom. That allows us to actually manage any kind of callable easily inside our own private section. However, we need more because at some point, people might want to copy a function. At some point, some people might actually call a standard function object. But we only store an abstraction. We don't really have anything to know the type. We have lost the information about the type. So we draw in another design pattern, the so-called prototype design pattern. The concept class inside actually provides a clone function that the model must implement. But that clone function implementation is kind of trivial because at that point we know full well what you need to do. That clone function now represents virtual copying. I can copy something where I just know some base type. Prototype indeed. And now you might have actually recognized the other design pattern that I've now basically described. Standard function itself is implemented by means of the type erasure design pattern. A very C++ specific thing to some extent. Other programming languages use it as well, but this is how we implement it in C++. At least this is one way. Type erasure is kind of a combination of the patterns that we've seen before, with, of course, the intent to combine all of these. So type erasure is first a templated constructor, then a completely non-virtual interface, but then a combination of the three design patterns: external polymorphism, bridge, and prototype. So you do realize there is a lot of design patterns. Indeed, a lot. By the way, if type erasure itself is interesting, I have the honor to also give another talk about type erasure on Thursday, which is a much slower, much more detailed introduction to the topic, but still a design analysis, something where we actually want to deal with why does it work so well? Why is this something that in C++ we want to do? We want to break dependencies. All right, so the takeaways for you. Design patterns are definitely not outdated nor obsolete. The standard library itself is full of them. There is hundreds of uses of design patterns. You just have to recognize them. And design patterns are pretty much everywhere. So it definitely, without doubt, helps to learn to recognize them and also to use the names to communicate the intent. That definitely helps to make the code clearer, to structure the code clearer. Okay, so in summary, design patterns are about dependencies and abstractions. Design patterns are also about intent. If I tell you I want to use a bridge, you should have a pretty good idea about which effect I want to achieve, how I want things to be decoupled. Design patterns are definitely not limited to object-oriented programming. That may be a leap because, of course, the original ones come from a book that actually provides object-oriented design patterns. But only some of them are truly limited to OO. Most of them are not. And they're definitely also not limited to dynamic polymorphism. They very well also work with static polymorphism. And definitely, design patterns are not outdated, and they're definitely also not obsolete. They're pretty much everywhere. All right. And so we do have approximately 10 minutes left, which I definitely can use to answer a couple of questions that you might have. Either way, at this point already, thanks for your attention. Okay, and there is a question by Nicholas. I have seen some say design patterns disappear when using functional programming. Is this them really saying you need less boilerplate to use them? Well, there is actually a talk by Ivan Kukic about functional design patterns this CppCon. I apologize, I do not know exactly when it will happen, but once again, Ivan Kukic, you will talk about functional design patterns. You might not use them in you might not use exactly these design patterns here, but there's others. So design patterns, as I said, are everywhere. There's definitely more than just the GoF patterns. There is many, many more sources to get to know them. Yes, of course, some boilerplate code may disappear. OO programming comes with a lot of boilerplate code. That's kind of part of the game, but still, there's many of them. So please check out the talk if this is interesting to you, because yeah, it definitely might help.